All right, hello again. So today should be a little bit of a shorter day. The material shouldn't be too heavy today. So today we're going to be talking about something called linear approximations and differentials. So here's first a little representation of what it is we're going to be talking about. So a linear approximation is kind of exactly what it sounds. It's a way to approximate a value using a linear function. So for example, if we're looking to approximate the function 1 over x at the point x equals 2, here is the function 1 over x. Here is a linear approximation that we will have created. And this is the point that looks like essentially the line is a tangent line. Um, and we would essentially be able to plug in the value that we are trying to approximate, and it would give us a very close solution. Now, if you zoom in very close to this point, say you do this on like a graphing calculator, that's exactly what we have right here. So you zoom in really close, as you can see right here, our values are so small. Um, you can see that at 2.1, the values are just a tenth off, or not even a tenth. These are a thousandth off. So it's very close when we actually use linear approximation compared to trying to actually compute this by hand, which would be very difficult. All right. So let's first talk about what linear approximation is. Let me move my face. Okay. So first recall that this is the equation of a line, y equals f of a plus f prime of a times x minus a. That is just the equation of a line. So what I want to point out in this right here is that we call the linear function L of x equals f of a plus f prime of a, x minus a. The linear approximation, I don't really call it the tangent line approximation. We will only use the linear approximation of f at x equals a. Sometimes you'll also see linearization, but again, we'll usually see linear approximation. So if you're looking to find the linear approximation, we are going to create this formula right here. So the value a is going to be the integer x value, the closest integer x value to the value that we're trying to approximate. So typically we'll try to approximate like strange numbers, not strange numbers, but just non-integers. Like we'll try to approximate, I think one of them, the first one, for example, is the square root of 9.1. And we know the square root of 9, that's 3. So it's probably going to be really close to 3, but the square root of 9.1 is probably hard to do by hand. So we're going to use linear approximation. So our a value is going to be the integer, and the x value that we use right here is going to be the actual 9.1 or whatever it is that we're trying to plug in. All right, so let's go ahead and actually do this example now. So find the linear approximation of f of x equals the square root of x at x equals 9, and use the approximation to estimate the square root of 9.1. So it does say x equals 9. While that is correct, we want to think about it as a equals 9. Just because of the formula that they gave us. We know that the linear approximation formula is L of x equals f of a plus f prime of a times x minus a. So we really want this x value to be this value right here. We want the a values to be the integers because you don't want to plug in 9.1 into most of these things. You do want to plug in 9.1 when you just have a single thing to plug it into, though. All right. So first, we will need to find f of a and f prime of a. And those are pretty simple considering we've kind of been doing that the whole semester. So I can move this back up here. The most obvious one is probably just to find f of a first. So f of a, where a is 9, is f of 9, which is a square root of 9, which is just 3. So that's pretty simple. Now for f prime of a, we first need f prime of x. So let's find the derivative. So if f of x is a square root of x, we know we can't take the derivative of a square root, so we need to write it as a fractional exponent. We know to write something as a fractional exponent. You write it as the power over the root for the exponent. The power here is 1 over the root here is 2. So to take the derivative, f prime of x equals 1/2 multiplied out front is 1 over 2x to the 1/2 minus 1 is minus 1/2. So this right here is going to be our derivative function. And because we have to plug something in, I'm going to rewrite this to make it a little bit nicer. So I'm going to write this as a single fraction. There's going to be a 1 in our numerator and a 2 in our denominator because of this right here. Now we see a negative in our exponent. We're going to want to make this positive, so I'm going to put this down here. And we know a square root is 1/2, so this is actually the square root of x. So 1/2 x to the minus 1/2 is the same thing as saying 1/2 square root of x. And I'm doing that because when I have to plug in 9, it'll just make it a lot easier to plug it in. So now we can do f prime of 9 equals 1/2 square root of 9, which is the square root of 9 is 3. 2 times 3 is 6. So this is 1/6. All right, so we found this, we know what A is. We can now just create our linear approximation formula. So L of X equals f of A, which we said was 3, plus f prime of A, which is 1/6, x minus A, which is 3. So notice how we haven't plugged in any values for x yet because we're just looking to find the formula first. Now, once we find the formula, we can go ahead and actually plug it in. So the linear approximation of 9.1 is 3 plus 1/6 times, well, let's see here. This, I am sorry, I wrote the wrong number here. A is 9, not 3. I wrote f of 9 there to be 3. This is 9. So we have 9.1 minus 9, and then we can just go ahead and solve this. So for this section, you are going to need a calculator. We aren't allowed to use calculators in this course, like on exams and stuff like that, but for this, we will need to use a calculator just because the numbers are kind of weird. So I will just give you the number. So this number is 3.0167 if you were to plug this into a calculator. And you do notice how this is very close to 3, which we know that the square root of 9 is just 3. So we know that this verifies that our answer is going to be correct. All right, so as long as we're plugging it in correctly, as opposed to what I did, make sure that A is just A and not f of A, we will get the right answer. All right, let's do another example. So this one says, find the linear approximation of f of x equals 1 plus x to the n at x equals 0. Use the approximation to estimate 1.01 to the 3. So this one's a little bit tricky because they don't exactly give you the values right off the bat. You kind of have to figure it out exactly what you're looking at. First, they give you n up here, but you see that you have a 3 here. And so what that tells you is that you're actually looking at n to be 3. And so you can also rewrite this as f of x equals 1 plus x to the 3rd, because this is what we're looking to actually solve for. And if we're looking for f of x to be 1 plus x to the 3rd, we need to figure out what that x value is. Because again, this says x equals 0. We're not going to consider this to be x. We're going to consider this to be a equals 0 based on the formula L of x equals f of a plus f prime of a times x minus a. So we actually want to know what x is. We know what a is. A is 0. Well, if I need to get to 1.01 and I know that this is 1 plus x, well, what do I have to add to 1 to get to 1.01? That's just 0.01. So that actually tells me that x is going to be 0.01. So they didn't explicitly give us the information, but we were able to solve just using the context clues from the question. So we have that x is 0.01, we have that a is 0, and we know that we've gotten correct numbers because a and x should be very, very close to each other. Otherwise, you can't approximate it. Now we can find the rest of the information. So f at a is f at 0, which is if you plugged 0 into our formula here, 1 plus 0 is 1, cubed is 1. All right, so we know that f at 0 is 1. Now let's go ahead and find f prime of x. F prime of x, we are going to have to use the chain rule here. So this is 3 multiplied out front, 3 times 1 plus x, subtract 1 from your exponent, and then multiply by the derivative of the inner function. But the derivative of the inner function is just 1, so you don't actually have to write that. All right, so knowing this, we can now find f prime of a. So f prime at 0 is 3 times 1 plus 0 squared is just 1. So that tells us that f prime of 0 is just 3. Okay. We have f of a, f prime of a, we know x, so we can actually go ahead and now just find our formula. So we'll always start by writing out the actual formula, and then we'll plug in after. L of x equals f of a, which is right here, it's 1 plus f prime of a, which is 3, x minus a, which is 0. So technically, you didn't have to write that. So this is the same thing as saying 1 plus 3x, which tells us that the linear approximation at x, which we determined to be 0.01, is 1 plus 3 times 0.01, which this is a pretty easy computation, is just 1.03. And we can kind of verify that this is true because if you took a to be 0 and you plug that in here, we know that it's 1. 1 is close to 1.03, so we do know that we're correct if you were to actually try to verify this solution. So linear approximation is 1.03. All right, let's look at one more example, and then we'll go ahead to talk about differentials. So find the local linear approximation. The word local doesn't really have much of an impact here. This is just because it's a continuous function that has an infinite domain. It's still just a linear approximation. To f of x at the cube root of x at, again, since this is an integer, this is not going to be our x, this is going to be our a. Use it to approximate this value right here. Okay, so what we know is that a is 8. We know that x is the non-integer value, which is going to be the 8.1. And then we can find f of a and f prime of a. We again know L of x is f of a plus f prime of a times x minus a. All right. So first of all, let's just find f of a because we don't actually have to do any calculus for that. So f of 8 is the cube root of 8, which is just going to be 2 because 2 times 2 times 2 is 8. So f of a is 2. Now we can find f prime of a. So first we need to find f prime of x. So first we need to convert this root to a fractional exponent because again, we can't actually take any derivatives of roots by themselves. So f of x is the cube root of x, which we can convert to a fractional exponent using the power over root rule. So the power here is going to be a 1 over the root here is a 3. So the cube root of x is the same thing as saying x to the 1/3. Now we can take a derivative. So f prime of x equals, multiply the 1/3 out front, x to the 1/3 minus 1 is the same thing as saying 1/3 minus, say, 3/3. So that's negative 2/3. So now we can go ahead and rewrite this a little bit because again, we need to be able to plug in a value and actually compute that value. So we have a negative exponent. I can bring that into my denominator. So we'll just have a 1 in the numerator. We'll have a 3 in the denominator from the variable out, from the constant out front. We will put this back into root form. So this is power over root. So we know this is a cube root of x squared, which tells us that f prime of 8 is 1 over 3 times the cube root of 8 squared, which is, well, the cube root of 8 is 2, so the cube root of 8 squared is 4. 4 times 3 is 12, so this answer is 1 over 12. So f prime of a, and I probably should have written 8s in here, but it doesn't actually matter, is 1 over 12. Now that we have all of the information, we can go ahead and write our linear approximation formula, which is f of a, which is 2, plus f prime of a is 1/12, x minus a, which is just 8. And now we can approximate the value that we're looking to approximate. So the linear approximation at 8.1 is 2 plus 1/12 of 8.1 minus 8. And if you were to do this calculation, I'm just going to give you the answer again. It's 2.0083. And we can verify that this looks pretty correct because we know that the cube root of just regular old 8 is 2. So the cube root of 8.1 is probably something really close to 2, like this answer right here, which it in fact is. All right, now we can start talking about differentials. So this is kind of a strange concept because we haven't yet talked about being able to do anything with dy dx. So what a differential is a way of estimating kind of the change of a function. So a function in small changes. If we consider that y equals f of x, which is just our regular old function notation, and it's some differentiable function, then we can obviously take the derivative of this function. So if you have y equals f of x, then the derivative of this is dy dx equals f prime of x. The idea of a differential is dy dx isn't like one term that you can't touch. It's not like the natural log of x or the sine of x. It's not attached to itself necessarily, as long as dx is an independent variable. So what that means is you can treat this as like a regular old fraction. Now you can't separate the d and the y or the d and the x because that is kind of just indicating what it is that we're looking at. But dy and dx are two separate things. So what you can actually do is multiply the dx to the other side. And what we have is that dy equals f prime of x times d of x times dx, where dx is the change in x and dy will be kind of like the change in y almost. So this is the idea behind a differential. So sometimes you'll be given like, here's a bunch of information, here's the differential, solve for this specific differential, which would represent the change, the small change in the value. So that's what we'll be looking at here. Again, it's not a very big topic. It's not something that will probably come up much, but it's definitely important to understand that we can separate this, the dy and the dx. And if you do take Calc 2, there will be times when you do have to use this idea of a differential and separate the dy and the dx. And a little bit later on, we will talk about, obviously this whole course is about derivatives. We will talk about something called an antiderivative, which is just kind of like the opposite of a derivative. It goes the other way. And you will have to use sometimes this idea to find antiderivatives, but that's a little bit later on in Calc 2. We won't cover that. All right. So let's just do a quick example. So it says for each of the following functions, find dy and evaluate when x is 3 and dx is 0.1. So all we're doing here, it's pretty simple. We're taking a derivative, we're multiplying the dx over, and then we're plugging something in. It's really not anything too weird or too strange. It's just moving some stuff around and plugging some stuff in. So a is x squared plus 2x. So we know that's y, which tells us that dy dx equals just a regular old power rule. This is 2x plus 2. Therefore, if we multiply the x to the other side, we get that dy, no fraction bar, just dy. If we multiply dx to the other side, we get that dy is dx times 2x plus 2. And if we're looking to find dy when x is 3 and dy is 0.1, then, well, dx is 0.1. X is 3, so it's 2 times 3 plus 2. So 2 times 3 is 6, plus 2 is 8, times 0.1 is just 0.8. So our dy is 0.8. So the differential here is 0.8. For b, we have y equals cosine of x, which tells us that dy dx, the derivative of cosine, we know that that's going to be negative sine of x. Since there's nothing inside of the x, we don't need to use a chain rule here. Because we know the dy dx is negative sine of x, we can multiply the dx to the other side, and we get that dy equals negative sine of x times dx, which is, well, if we have values to plug in, we can just plug it in. So this is the negative sine of 3 times 0.1. And there's no way of simplifying this because the sine of 3 is a decimal value. So you can just kind of leave it like this. All right, that's kind of the idea behind a differential. And this will be a very small number here. All right, and this is, again, a little visual representation of the idea of a differential. So we could use differentials to approximate the change in y from some value a to some value a plus dx, where dx is some small value. So we're just kind of looking at a very small incremental change to find dy. Again, this topic isn't going to come up a whole bunch, but it is important to know that this is something that we can do. And this is a little representation of what that means. All right, so this is the last problem of today. Again, this was a little bit of a shorter day. So now we're looking for the change in y and dy. So essentially we are going to be comparing these two values and confirming that they are in fact very close. The differential is close to the actual value of the change in y. So we can start by computing whichever one we want. We could do the change in y first. So if you remember, the change in y is if you even think back to like the slope formula, it's the change in y over the change in x, which is like f of one value, so f of b minus f of a or something like that. So if we know that the change in x is 0.1, we're always going from left to right. So if we're starting at 3 and we're changing by 0.1, then we are going from 3 to 3.1. So that's what this kind of notation means. So we are increasing by 0.1. So what we'll have to find for the change in y is going to be your f value, since that's the y, right, of the larger value, 3.1 minus f of the smaller value. And we can go ahead and actually compute those values. So that's going to be, let's see here, 3.1 squared plus 2 times 3.1 minus, and I will put parentheses around this because we're subtracting a quantity, 3 squared plus 2 times 3. And this is going to be equal to, let's see, I have this written down right here, 6.192. So the change in y is 6.192. That's like the actual value that we would get. Now let's find the differential. So we can take the derivative of this function. So dy dx equals, the derivative of this is 2x plus 2, which tells us that dy is 2x plus 2 times dy. And we can plug in these values. So this is the same problem as before. So we got 2 times 3 plus 2 times 0.1. And, oh, you know what? I actually have a different question in my notes. So this value that I have here is off. So let me erase this value and I will actually compute that value by hand. So first, let's get this value. So this is 2 times 3 is 6, plus 2 is 8, times 0.1 is 0.8. And this value here, let me actually go ahead and compute that. So given this, let's see, we have 3.1 squared plus 2 times 3.1 minus 3 squared plus 6, which is 0.81. I apologize. I changed my second value a little bit. So we have 0.81 and 0.8. So the change in y is actually 0.81. The differential, if you were to compute it, is 0.8. They are very, very, very close. And that's exactly what we're looking for here. All right, so this is the end of what we're going to be looking at in this section. If you have any questions, as always, let me know. And I will see you for the next video.